Hello, everyone. My name is Ricard Peterson, and I'm leading the research and development efforts for the high frequency and signal integrity electromagnetic solvers at Ansys. Today, I will provide you an overview of Ansys HFSS solver technologies. As you can imagine, there are lots of different technologies that goes into these solvers. So today, I mainly will provide you an overview of the distinct different solvers that are available, as well as a little bit more in depth on some of the key technologies of the frequency domain following element solver that is the most commonly used solver. On this slide, I cover the different solvers we have available. First, as I just mentioned, the frequency domain finite element solver is the most widely used solver we have. It's a general purpose solver targeting complex geometries as shown here, where it's a board and a package in a board with lots of details, highly complex. Finite element frequency domain finite element analysis is very well suited for this type of application. Then we have a time domain finite element solver. It's also general purpose, but it's best suited for studying transient signals, as you see here. We have an incident wave impinging on a laptop to study, for instance, EMC effects. Then we have a frequency domain integral equation solver, which is sometimes referred to as a method of moment solver. It's less general purpose, and it's primarily used for electrically large metallic structure. It can include some dielectric, but electrical large metallic structure is the key application area. And then we finally have an SPR plus solver. It's an advanced ray tracing solver targeting electrically very large scenarios, as you can see here on the bottom right, where we have an automotive radar simulation going on for a complicated intersection. Next, I would now talk about some HFSS foundational technology breakthroughs for the frequency domain finite element solver. And those are 4 different ones. I'm going to first list them here and then get into some detail, a little bit more detail in the subsequent slides. So the first major breakthrough is the Spurious free vector basis functions. This really enables reliable finite element solution of Maxwell's equations. And Zoltan Sendiz, who was the founder of Ansys, that subsequently got acquired by Ansys in 2008, was the inventor along with Barton, and their paper is shown here. It's a seminal paper from 1987. And next is the automatic adaptive meshing for accuracy and efficiency. Again, Sendiz and his collaborator Shenton started this early in '85, and we have ever since improved this process, and I'm going to speak to that a bit later. Next is the Transfinite Element method. It enables highly accurate and efficient extraction of network parameters, such as the SYC matrices. And again, Sendiz and his collaborator Lee, in this case, published their paper on this method in 1988. Finally, the domain decomposition method, which was mainly worked on the initial versions in 2000, and they published this, Sendiz with his collaborator Lee and Vovakis published this paper in 2006. And it enables distributed memory computing efficiently. So you're no longer restricted to one computer. You can solve a problem over computer to expand the RAM footprint across many computers and many cores. And this technology is also key for many of the advanced solver features that I will discuss later. To put these technologies into some context, I want to briefly introduce the finite element method for you guys. And I'm going to do this in the context of Maxwell's equations, and more specifically, the second order Maxwell's vector wave equation shown here, which is exactly what we solve in HFSS. And you can simplify that to be an operator L operating on electric field E equal to some forcing function F. The first step is to expand the electric field in terms of basis functions, Wj seen here with coefficients alpha. Those are unknown coefficients that we're going to solve for later. And these basis functions, they reside in finite elements. And in HFSS, those finite elements are tetrahedra. And so the next step is to plug that approximate expansion of electric field into the equation above. And you see you will have a residual. And because you don't have the exact solution, it's going to be some residual. And the better approximation is, the smaller the residual will be. So to get the n equations and n unknowns, what we do is we weight that residual with basis functions across the mesh with all these tetrahedras. And by doing it this way and setting it to go 0, we can finally arrive at a matrix equation, AX equal to B, where A is the matrix, and for finite element analysis, the matrix is sparse. And that's a key attribute, because that can be taken advantage of when you solve this system using either a direct solver or an iterative solver. So back to the main breakthroughs. So the spurious-free vector basis function was first published in '87 in this seminal paper by Barton and Sandys. Since then, HFSS has been enhanced with hierarchical vector basis functions. They're also spurious-free. And each element can use a different polynomial order. And by doing that, we can vary the polynomial order across the mesh, and that's indicated by P, and then we can also change the mesh, the element size across the mesh, which is indicated by H. So that's an HP mesh refinement, and I'm going to discuss that a little bit later. But having hierarchical vector basis function is critical in order to do that. And the paper they published on that, again, Sandys with the collaborators Sun and Lee in this case, was published in 2001. So onto automatic adaptive meshing, which is probably the most famous technology that we have for HFSS, and it's been a key to its success. The mesh is automatically created and then adapted according to electromagnetics. So the physics describes the mesh, not the other way around. And this technology is really key for the HFSS gold standard accuracy. And I'm describing that here with this animation on the left. So we start with initial coarse mesh, and we solve the fields on that mesh, and we estimate what the errors are in some manner, which is the proprietary error indicator with over 3 decades of improvements, and it will tell us where we should refine the mesh. We refine the mesh and solve again on the next mesh, and again estimate the errors, refine the mesh, and so on until we finally get to converged mesh, as this animation indicates. So this error indicator drives both the H and the P refinement. Again, H refinement means that we are changing the element size in the proper locations to get better accuracy. And the P refinement, we selectively change the order of the basis functions. And finally, the mesh adaptation relies on proprietary fine-tuned mesh routines, so that when we refine the mesh, we get nice, efficient meshes at each step. Here's a flow chart that describes this method. We start with initial mesh, and then we provide some automatic mesh seeding and some P refinement as well. And then we solve our first solve. And first go around, you're not going to satisfy the convergence criteria, because it's based on comparing the results for 2 consecutive meshes. So then we compute the errors, and we refine the mesh accordingly. And then we also distribute the orders across the mesh as another type of refinement. Solve again, and then now the second time around, we can now check the convergence criteria. Has it converged? If it has, we stop. If no, we continue the process until this mesh has converged. And the key to this algorithm is that it provides highly accurate results with a minimal mesh. It's pretty straightforward to get high accuracy results as long as you have the right ingredients on the finite element method, which we do, by making a very dense mesh and higher order of basis function. But this is going to be very inefficient. So this is the key here. We obtain this mesh efficiently that provides accurate results. Next, I want to discuss the transfinite elements. And by doing that, I illustrate here a model, which I call the physical model. Of course, everything is animated using HFSS here. But imagine you have this physical model. You have some match generator at the end of the transmission line that feeds this filter structure. And in HFSS, we're going to put a port here that's indicated. So we don't need to model this long transmission line because that is assumed in this port formulation that is used in the transfinite elements. So part of transfinite element is that we expand electric fields in terms of the eigenmodes of that port structure, meaning the modes that would reside in this transmission line here. And we expand that on that port surface, we're going to expand in terms of both known incident alpha coefficients, that's how we excite the structure, and then the unknown beta, the scattering coefficients. And that's how you get the scattering matrix that relates the incoming coefficients with the scattering coefficients on all the ports in the structure. And another key component here is that each mode on that port serves as a basis function. It makes it very efficient to represent the ports. And I just want to make a comment here also that this model was obtained for us courtesy of SYN matrix. So to summarize a bit more here, so the technology is unique by HFSS and was introduced in this paper back in the 80s. And the port modes are the basis functions on the port surface, makes that representation very efficient. And part of the formulation is an exact numerical truncation. What that means is any fields that get scattered back to the port from this 3D structure are perfectly absorbed, so it doesn't introduce spurious reflection that goes back into the 3D domain. So these things together then yields a very low noise floor with high computational efficiency. And by using the transfinite element method, we can make it even more efficient when we're only solving for the S parameters, meaning you're not going to look at the fields as illustrated here. You just get the S parameters on the ports. That is very efficiently done, and I'm going to mention that a few more times. And also the method is to use PML back ports. They are typically less accurate. It's still pretty accurate, but not as accurate as the transfinite element method. And it's less efficient, especially when the port just need a handful of modes to be accurate. In using this method, you also does not get much boost when you're only interested for solving for S parameters. Finally, the last major breakthrough is the domain decomposition method. And the paper I'm showing here was published in 2006 by Sanders and his collaborators. And to illustrate what it does, it's here on the right. So you have a computational problem you want to solve with this aircraft. We mesh it with a tetrahedral mesh. And we break that mesh up into 5 different domains, for example. And that's all done automatically, by the way. And then each computer can do a lot of the finite element work just for one domain. So you have 5 domains, 5 different computers. And that enables you to solve really huge problems because you're no longer bound to one single computer. And one key aspect of this method I want to stress here is there's no simplified field coupling at the interfaces. There's some special treatment related to domain decomposition, but there's no assumption of what the field properties are. And that's key because there's some other domain decomposition methods where they have a certain assumption of the field at the interfaces. And if that assumption does not obey, then you're going to start introducing errors. Next, I want to discuss the matrix solvers used to solve AX equal to B. So domain decomposition is a way of solving this, but it relies on both the direct and iterative solver that I'm going to discuss next. So the most commonly used solver in HFSS is the direct matrix solver. And it's a mature technology that we developed at Ansys over the last 2 decades. And it's been proven ever since by lots of users. It is an efficient multifrontal implementation to solve the system. And just to give you a flavor of what a direct solver is, this is not necessarily unique to our implementation here. You're typically going to factorize the matrix A into 2 different matrices, L and U, that are multiplied. And L is a lower triangular matrix and U is an upper triangular matrix. So all the important work of a matrix solver is to get those factors, L and U. After that, it's straightforward to solve AX equal to B. via a forward-backward substitution method. And you can see that quickly here. If you substitute LU for A, and then you recognize the UX is just another vector Y that is currently unknown, and you start solving for Y. And due to the properties of L, you can easily get the first entry of Y. So this is in the forward direction. We have this formula here. And then you get Y2, the second entry like this, which involves the first entry of Y, and you keep going like that forward. So you get until you get to Y with the last entry of Y, N, let's say in general. So now you have the vector Y, and now you're going to solve UX equal to Y to get the desired unknown vector X. It's related to the coefficient vector of the basis function of the finite element method. And in that case, you start backwards because of the property of U. So you solve for the last entry of X, shown here, and then you go to the next to last entry, as shown here, and so on. So that's the backward substitution part. So that's general for any direct matrix solver like this. So the key is to compute the L and U efficiently and robustly. So basically, direct matrix solver in HFSS, the solution is guaranteed within a finite set of operations. It can be memory consumption. It can be, it can be CPU consumptive. Take lots of steps for huge problems, but you will get a solution. That's one of the strengths of it. It's very, very robust. And it's also efficient for a very large number of excitations, where an iterative method is less efficient, that I'm going to talk next. And this particular solver also supports a novel implementation of mixed precision to save memory. And that's by computing storing the L and U matrices in single precision, and then solve for the X in single precision, and then upgrade it to a double precision accuracy via some iterations in a very efficient and robust manner. And finally, it's a very efficient way to solve S matrix only when the transfinite element method is involved. And if you're only interested in S matrix compared to solving for the full fields, you will typically use around three times less memory and have a decent boost in performance as well. But using the less memory is critical for frequency sweeps, which is very commonly solved for in HFSS. You can solve more frequencies in parallel, and therefore boost the parallel efficiency. And finally, the solver itself supports HPC, and it's been parallelized both for shared memory and distributed memory applications. And it's therefore available for clusters, including the Ansys cloud. Next, an brief overview here of the iterative solver, which is a great alternative to the direct solver for memory limited situations, such for instance, when you have only one machine and you're solving a huge problem, the direct solver cannot solve due to the limited memory. In this case, there's no factorization occurring. Instead, it's an iterative process where we start with the initial guess of the solution vector X, shown here, X equals X sub 0. And then each subsequent step, we make a correction to the previously solved vector, xn, and then equal to xn minus 1, plus some correction. And the correction involves a transformation f operating on the residual vector, rn sub minus 1. And this residual vector is just shown here. Basically, shows the residual error between the solution and the right-hand side vector b. So if you have no residual, you have the solution. So this process keeps on iterating until you get a desired error tolerance of the residual. And the operator f takes different form depending on what exact type of iterative solver you have. And you have different types, but this is the general form. And this process is recommended for moderate number of excitations, since each solution has the solution due to each excitation has to be solved separately. Most iterative solvers use a preconditioner, indicated here by M. And ideally, you're having precondition as the inverse of A, and then you have the solution, because then you know what X is. But you want to do something that's close to that, but cheap to compute. So that's the key. For HFSS, we use a multi-level preconditioning, and that's enabled via the hierarchical vector basis functions. So basically, we have typically 3 up to second order The zeroth orders mean the curl of E is constant, but E has more of a linear dependence, and the first order means curl of E is first order, and then the second order means the curl of E is second order. So we do this by completely factorizing the zeroth block, and the other two blocks have approximate factorizations to represent the inverse. So by doing this, we have a very efficient preconditioner that is relatively cheap, but will allow the iterations to convert quickly. Next, I want to talk about the advanced solver options in HFSS. So here's a diagram illustrating that. At the bottom, when the electrical size is not huge, you can solve on almost any problem you want with finite elements. So I show here on the x-axis, the geometry and material complexity can be pretty much as complicated as you want it to be. And today, when you have access to clusters or the cloud, the electrical size can also be quite large. But at some point, you're probably going to start running out of steam with this, even in today's compute capacities. And then a good option is the integral equation method, which doesn't have as general geometry material dependence, cannot handle super complicated cases, but it can handle electrically large ones, primarily metallic, as mentioned before. And finally, we have the SPR plus solver that can handle electrically huge problems. And again, the geometry and material complexity has gone down a little bit further. And then we have the domain decomposition method that combines all these methods. And I'm going to talk about that next. So first, very briefly on the integral equation solver. As I mentioned a couple of times already, it's well suited for electrically large open region problems. And it can handle dielectrics, but it's mostly recommended for metallic structures. And this solver solves two equations, the electric field integral equation or the combined field integral equation. It depends on the type of geometry you try to solve, which one is used. And that's out of the user's control, that's automatically detected. And it's using the mixed potential integral equation. These integral equations that always leads to big matrices are dense. So in FEM, as I mentioned before, they're sparse, and you can exploit that when you with a direct solver and iterative solver to efficiently solve those systems. But in this case, we have a dense matrix, and to make that efficient, we make accurate approximation of this dense matrix to the point where it's not practically any difference compared to if you solve the full dense matrix. And the two methods we use is adaptive cross approximation and the fast multiple method, and either one of them has benefits in different scenarios, and I'm not getting into that here today. And both of these fast methods are parallelized, and they work both for shared memory and distributed memory applications. Next, the SPR plus solver. Again, you can solve these huge scenarios, as I show here on the right, and shooting and bouncing rays is what SPR stands for. It's an asymptotic technique, and it is complementary. The previous methods I spoke about are all full wave solvers, meaning they introduce no inherent approximation to solving Maxwell's equations. And the asymptotic technique does introduce some inherent approximations. And the most well-known one is the PO, physical optics, where the currents induced on a structure is assumed to be just a function of the incident field. And SPR extends that by allowing the incident wave to reflect off this structure, and it sets off basically rays, as you can see here. And the direction of those rays are dictated by geometrical optics. And there's lots of detail that goes into this solver, but at a high level, that's basically what it is. And the geometry complexity goes down. It's more expecting large, smooth surfaces, not tiny, small details. But the dielectric, the material properties can be pretty general, including dielectric and magnetic stacks, Fresnel table imports, and so on. The plus part of SPR plus, that is, in addition to SPR, we provide additional physics to enhance the accuracy. So we have both physical theory of diffraction and uniform theory of diffraction to improve the physical representation of edges. And we also have what we call creeping wave, which enables the wave to go beyond the shadow boundary. So for physical optics, you have a lit region, that's what the source will see. And then you have a shadow region, we just simply set the field to 0. For this creeping rays, we don't just set the field 0 in the shadow region. We allow those waves in a particular way to extend into the shadow region. So the driving philosophy of SPR Plus is that we radiate painted currents to field observers, and all models, mechanisms, they all work together to improve the accuracy. So SPR and the PTD, UTD, and creeping wave, if they're all used, they all enhance the accuracy of the solution. Next, I want to talk about the hybrid solver using DDM technology. And the first one is the Phoebe solver. It's basically, here I'm showing 2 Phoebe domains, where in each domain I'm find the element interior, and then on the boundary of those domains, I'm solving an integral equation. And those 2 domains you see, they are coupled together via this integral equation. So it's a very efficient way of solving open region problems when you have lots of empty space, as indicated here. And they're fully coupled, there's no approximations. And then you have IE regions, which I mentioned using the integral equation solver, primarily targeted for metallic structures. And then the cool part is that you can combine them. You can combine Phoebe and IE, for instance, shown here. So the horn antennas are each modeled with a Phoebe, and they can be fully coupled. And then the dish is modeled with an IE region, which is fully coupled to the Phoebe horn antennas. And there's no approximation introduced here. You can substitute, for instance, the IE region with an SPR plus region. In that case, it's one way. The horn antennas can be fully coupled, but they interact one way to SPR plus, meaning the SPR plus solutions do not influence the horn antenna solutions. And next, the 3D component array solver is recently introduced. And it's also built on the advanced DDM solver. In this case, we can do independent meshing for each unique 3D component. So this is primarily for large antenna arrays. So you can see here the UI, the user interface on the left, where you can place various different components. In this case, you have 14 different components, and you indicate here where you're going to place them. Okay. And each unique component, so 14 in this case, are going to be independently meshed, and then you can also independently adapting the mesh for those components to quickly get to the point of solving the full array. Instead of meshing the entire array separately and then adapting the mesh for that entire array, it's much more inefficient for these huge problems. And then the transient problems, we have a transient solver, as I mentioned in the beginning, and here's some examples of when that's applicable. You know, lighting stride analysis, EMC analysis, maybe even radar cross-section analysis is shown on the upper right, left. And also TDRC, when you look at the TDRC of a transmission line, for instance. So that's a transient phenomena. And it's highly accurate. It's also finite element formulation. And it's also using the same adaptive mesh as frequency domain solver, including higher order basis function with 2 solve options. One is a hybrid, and it's implicit and explicit combined together with a local time stepping. It's very efficient for electric large structures. Now we have a fully implicit scheme, which is unconditionally stable, which makes it very efficient to solve electrically smaller but highly complex structure. Finally, I want to just make a point here that we have, over the last 10+ years, all the solvers has been fine-tuned for HPC performance. And for instance, the finite element solver now can distribute all the relevant solve processes, such as matrix assembly, matrix solver, field recovery, frequency sweep, and variations. So it's extremely well parallelized in that regard. And in the next talk, a review of HPC technologies in Ansys HFSS, Matt Commons is going to go over a lot of this HPC technology we have available now in Ansys HFSS. And that concludes my talk, and thank you very much for your attention.